all of these. Yeah, opposite way. From the diagrams, it was like.
So if the
Current is looping around this way, then the right, you curl your fingers in the direction of the current, and that will tell you the direction of the field that induces. Okay, so
Yeah.
that the only way we know about like the direction of the field is just knowing which way the current will go based on the area's potential.
yeah, I guess we're gonna do some examples today. Maybe it'll clear it up. So
Or is that kind of like what's going on today?
we'll review it. We kind of wrote down Lenz's law right at the end of last class, so it's the first thing we'll do today.
Oh, okay, thank you.
All right. Good morning, everyone. Welcome to the last day of this 121. So we have our last homework due tomorrow, and then end of term survey link on Canvas. So you have to complete that today. I will take the link down sometime, probably tomorrow morning. So just make sure you get that done. It's a free half mark towards your final grade. And we do use the results to try to improve the class if we can. So today, what I want to do is we're not going to cover new material. I just want to summarize the important results that we got last time. So we'll do a summary of Faraday's law and Lenz's law, and then we'll look at, we'll briefly look at an important application. And then we'll run through some example problems. I have more example problems than we can finish in today's class. So what I'll do is we'll work through some of them, as many as we can today. And then I'll just write out the solutions to the others. And so if you want to see those solutions, you just go and look at the notes after they get posted to the course website. Okay, so one of the major results that we got last time was Faraday's law, which says that if you had a changing magnetic flux, so the derivative of the magnetic flux with respect to time is not zero, then you get an induced voltage through some loop. And the way you would calculate it is you would just calculate the time derivative of the flux. In general, the magnetic flux is given by this integral of B dot dA. But it's often the case that the situation is more simple than that. If we have a flat surface and a uniform magnetic field, then the flux is just going to be B times A times the cosine of the angle between the normal vector to the area and the magnetic field. And so if they're parallel, then it gets even more simple because then the cosine of 0 becomes 1. And so what we said is that we could actually change the flux through a loop in 3 different ways. One way to do it would be to take this scenario here where you have a bar magnet next to a little loop of wire. I could increase the flux through the loop by increasing the strength of the magnetic field. One way to do that would be to take the bar magnet and take the North Pole and move it closer to the loop. Or I could decrease the magnetic flux through the loop by pulling that bar magnet further away. So that's one way of changing the magnetic flux. The other way to do it is, if I had that picture, I could keep my bar magnet fixed in place, and I could take my loop of wire, and I could take the loop, and I could pull it so that the loop closes. So we could start with a circular loop, and then you stretch the wires so that they close, and you effectively take the area from some large circular area to 0, and as you change the area of your loop, you change the magnetic flux through it. Motional EMF was another way of changing the loop area where you had a conducting bar sliding along a conducting track. And then the final way to change the magnetic flux is we're going to keep the shape of the loop the same. We'll keep the bar magnet fixed in place, so the strength of the magnetic field is not changing. But we can then change the angle between our loop and the magnetic field. And so imagine taking this loop and spinning it around this axis. Then whenever the loop has its plane perpendicular to the magnetic field, you'd have the maximum flux. When the plane of the loop is parallel to the magnetic field, you'd have 0 flux. And so as it's rotating, you'd constantly be changing the flux through the loop. And so you'd have this constant induced EMF, which would create a current in the loop. So those are the 3 ways that we could change magnetic flux. And we've talked about examples of each of them. The very last thing we did at the end of class on Monday was to talk about how do we determine the direction of the induced magnetic field and the induced current. This is given by Lenz's law. I don't think we called it Lenz's law in the last class, but we wrote down a result like this. So if the magnetic flux through a loop is changing, you're going to get an induced current, and that induced current creates its own magnetic field. We've been calling it B induced. If the flux through your loop is increasing, the induced magnetic field will tend to oppose that increase. It tries to maintain the flux that was there originally. And so if you have an increasing magnetic flux, the induced magnetic field will be in the opposite direction of the original field that was already in place, so that it opposes that increase in the flux. On the other hand, if the flux through a loop is decreasing, then again, Lenz's law says that the induced magnetic field that gets created will tend to try to maintain the original flux that was there. So if the flux is decreasing, the B induced is going to tend to increase the flux to bring it back to where it was. And that means the induced field would be in the same direction as the field that was already in place. And we're going to see some examples of this today. Okay, so the summary of Lenz's law is that the induced magnetic field has a direction that tends to maintain the original magnetic flux. So if the flux is decreasing, then the induced field tries to bring it back up. If the flux is increasing, the induced magnetic field will try to bring that flux back down to where it was. Okay, so what I want to do today is I want to start by just talking about some an important application of Faraday's law. And it's all going to be about electrical generators. And so here is a schematic of kind of a simple design of an electric generator. We've got a little structure that's supposed to be like a magnetic field. So this red section is going to be the north pole of some magnet, and this green section is the south pole. And so we get magnetic field lines that are pointing from the north pole down towards the south pole. So the magnetic field direction is downwards in this picture. And then we have this loop. It is a single loop of wire. You can see it's got like a little hand crank attached to it so that we could rotate this about an axis. And then there's some angle denoted here, this angle 5. So let's imagine that we start with the loop in this orientation. And then we rotate the crank wheel so that we increase the angle 5. So that means this loop of wire is going to become sort of more vertical. And as it becomes more vertical, we'll get less and less magnetic flux through this loop of wire. And so if there's a decreasing magnetic flux, then B induced will try to oppose that decrease. So should B induced point down or up? We're going to try to maintain the flux that was there. The magnetic field is currently down. The flux is decreasing. So should B induced be up or down? B induced. Do I want to go down or up? Who has a yes? Yeah. You want to go up? Who wants to go up? Okay, a couple who thinks it should be down. All right, so more people. So we want it to go downwards because we're going to try to maintain the magnetic flux that was already through this loop. And if the loop is going upwards, tilting upwards, we're getting less and less of those original magnetic field lines passing through it. And so we're going to try to add extra downwards fields to compensate for that lost flux. And so B induced is going to be downwards in this case. And if it's downwards, we could use the right-hand rule to figure out what direction must the current be. So I put my thumb down in the direction of B induced, and my fingers are curling. If I look from above, my fingers are curling in the counterclockwise direction. And so we must have an I induced that is going around this loop in this direction. So these are all of our I induced, right? And so let's see, I do my right-hand rule, I curl my fingers in the direction of this current, and the B induced is kind of downwards. It wouldn't be exactly downwards because our loop is not horizontal. So it's going to be tending towards being downwards. And so it'll look something like this. So our B induced is going to be perpendicular to the plane of the loop, but it is increasing the flux in the downwards direction. Okay, so what you could imagine is if I was to crank this in the other direction so that the flux was increasing, then I'd want my induced field to be in the opposite direction to oppose that increase, and the current would switch directions. So as you crank this wheel around, the flux through the loop is sometimes increasing and sometimes decreasing. And that means as I spin this, the direction of the induced current would be changing all the time. Every time we go through 180-degree rotation, the current would change directions. And that happens all the time in the actual electrical generators that are used in like hydro dams and things like that. You're spinning a coil of wire through a magnetic field, and the current is switching direction all the time. That's why if you were to measure the voltage coming out of your outlets in your home, it's not a constant voltage, it's a voltage that's oscillating all the time. So it's changing direction. It's positive half the time and negative half the time. And that's because of this design of the generator and the flux going from increasing to decreasing to increasing to decreasing. Okay, so here's a picture of a coal plant. And so what I want to do is I just want to look a little bit at some of the details. Get rid of this. Okay, that looks a bit better. So I want to just look at some of the details of the design of a coal plant. So this is just a picture of an outside of a coal plant. And so here's a schematic. And we won't spend too much time on it, but let's look at some of the details. So what we have is a little supply of coal. So we're constantly dumping coal into this burner. And so the coal is being burnt. And so this is where all of the exhaust from the burning coal comes out. And this is the part that is bad for the environment, the greenhouse gases. Okay. So inside this burner, we have this long kind of windy pipe. So there's this long windy pipe, and there's a supply of water entering this pipe that goes through this long windy thing. The reason the pipe is so long and windy is that we just want a large volume of water inside this hot burner. And the burner heats the water so that it becomes steam. And that steam is then pushed through this turbine. So the turbine is just a bunch of blades, like a prop on a boat motor or a propeller on an airplane. And you're just rushing the steam past these turbine blades, and it causes the turbine to spin. So you're using the high pressure steam to spin this turbine. And then that turbine is connected to the electrical generator. And the generator is just a big coil of wire that's spinning inside a magnetic field. And as it spins, the flux is constantly changing through these coils of wire. And that's where your induced voltage comes from. Okay, what they do is after the steam has entered the turbine and spun the turbine, that steam cools off and it condenses, and then it just gets fed back into the burner where you're burning your coal. So it gets reheated and circulated again. So to cool that hot water, they take water from a reservoir and they just run the steam through this region of space that has the cool water. And so the steam heats that cool water, and then that warm water then ends up over here. And then you just get a bunch of sort of lower temperature steam coming out of this big stack. Okay, and so in essence, that's what the coal plant is. The part that actually makes the electricity is all based on Faraday's law, and it's from this generator that is spinning due to this turbine. And so all of electrical generation is based on this principle. The only difference between, say, a coal plant and a nuclear plant is how they heat the water to make the steam that spins the turbine. So here's the nuclear power plant from Springfield in The Simpsons. And, you know, I won't show you the details of what's inside, but a lot of it is similar to what we see in the coal plant, except for what they do to heat the water is they take uranium, which is an unstable isotope, uranium-235, you fire a neutron at it, and it causes that atom to split. It splits into two lighter elements and a bunch of energy. That energy is what's going to be used to heat the water. So there could be additional neutrons come and they hit these lighter elements, and there's further splitting. And so every time you split these atoms, then you get a little bit of energy. Well, a lot of energy is released, and that energy is used to heat the water. So the waste in a nuclear power plant is all of this stuff that comes out of here is just sort of used steam, hot water. And so that's not particularly dangerous. It's taking the spent nuclear fuel and then storing that after it's been used. So that's the issue. Okay, in BC, what we use is mostly hydro dams. And so what you end up with is you've got a region where you have water at the top of a hill, so it has high gravitational potential energy, and you let that water come down the slope. They call it a penstock. And so as it comes down the slope, it's losing potential energy and gaining kinetic energy. That fast-moving water is sent through a little turbine. It spins the turbine again. That's connected to some coils that spin in a magnetic field, and that's how your power is generated. Okay, and so here's your generator here, and it feeds the signal to some transformer. Transformer can be used to step the voltage up or down, and then that just gets distributed to the cities and homes and so on. Okay, here is an actual hydro dam. It's kind of near Maple Ridge / Mission, a little bit west of us. And so here you can see the reservoir water at high elevation, high potential energy. It comes down, and you can see the water's kind of rushing out here. So this is after it's gone through the turbine and spun it up, okay? And then so here is, you know, all the transformers and stuff that will be used to set the voltage levels before it's sent out to the different homes. Okay, so that's located here. It's on the map. Where do we live? We live over here, and here's that hydro dam. So it's probably about 80% of the way towards Vancouver if you wanted to see it. Okay, good. And then, oh, I had some pictures here that I don't see anymore. Okay. What we'll have to do is, let's see if I can find what I wanted. Nope, they're not here. Okay, what I'm going to do is I'm just going to delete all of this stuff and we'll rewrite it all. Oh. Okay, so what we're going to do is we're going to work through some examples here. I thought I had populated this with blank pictures, but I obviously thought wrong. Okay, so the scenario is the following. We have two coils of wire side by side, coil 1 and coil 2. In coil 1 on the left, we have a current I. And the question is, what is the direction of the induced current in coil 2 if the current in coil 1 is increasing, if it's decreasing, or if the current in coil 1 is constant? Okay, so let's do part A. So for a loop of current, the direction of the magnetic field is given by the right-hand rule. Okay, so let's see, coil 1 has a counterclockwise current. And so I'm going to curl my fingers counterclockwise, and my thumb points out of the screen, And so the magnetic field of coil 1 is coming out of the screen. Okay, now what we know is that the magnetic field due to a current loop looks a bit like a bar magnet. And so the fields are going to be coming out and then looping around and then coming back in. And so they're looping around like so. So this is the magnetic field due to that first current in coil number 1. Okay, so through the second coil, that magnetic field is pointing downwards. So B due to coil 1 is downwards through coil 2. All right, so now we have to think about if we have the strength of this current in that first coil is increasing, then we have increasing magnetic flux in the downwards direction through the second coil. So if I is increasing, then the flux through 2 is increasing in the downwards direction. So by Lenz's law, B induced in 2 is, so we want to try to maintain the flux that's in coil 2. So imagine we turn on the current, we have some flux in coil 2 that's pointing downwards, and then we start increasing the current in the first coil so that we're increasing the flux in the second coil. Should the induced field be up or down? Up from Zoom, and that's correct. So we're going to try to maintain or oppose the increasing flux. So we're going to maintain the original flux by opposing the increase by having an induced field that is upwards. So by Lenz's law, B induced in 2 is upwards to oppose the increase in the magnetic flux. Okay, so if B induced is upwards, then by the right-hand rule, I put my thumb in the upwards direction and my fingers loop around, if we look from above, in the counterclockwise direction. And so we must have that our current is in this direction. So I induced to make the B induced that's upwards has to look something like this. I induced. So we have this counterclockwise current. Okay. I won't write it down so we can go to some other problems, but if the current in the first coil was decreasing, we would have a decreasing flux in the second coil. And in order to maintain or oppose that decrease in the flux, B induced would be downwards and the direction of the induced current would change, would be the opposite direction that we drew there. For part C, if the current in the first coil is constant, what's happening to the flux through the second coil? Is it increasing, decreasing, or constant? If I is constant, then the magnetic field is constant and the magnetic flux through 2 is constant. since the induced EMF is the derivative of the flux with respect to time, if phi is constant, then it's not changing with time. So d phi dt would equal to 0. There'd be no induced voltage, no induced current, and no induced magnetic field. And so in this case, the induced EMF is equal to 0, I induced is equal to 0, and B induced is equal to 0. So we need a changing magnetic flux to induce a voltage, current, and magnetic field. Okay, good. So let's do a second example. I'm going to erase all of this stuff. Okay, so could probably cut this. No. Okay, good. So here's a similar problem. The only thing that's different is that instead of having two coils side by side, we have a long straight wire carrying some current I and a coil to the right. So let's figure out the magnetic field due to the current in the wire. I put my thumb in the direction of the current, and my fingers tell me that the magnetic field is coming out of the screen to the left and going into the screen to the right. So we have a magnetic field that's looping around this current in this direction. So here's the magnetic field. So over here on the right-hand side, we have magnetic fields that are coming out of the screen. And then on the right-hand side, where we have the loop, we have the magnetic field going into the screen. So this is the same question. What happens if the current increases or decreases or stays constant? The stays constant part C is the same as the last problem. If the current is constant, there's no change in the flux through our loop, and there's no induced current, no induced magnetic field. Let's do part B this time. So if I is decreasing, then the magnetic flux through the loop, our coil, is decreasing. That means B induced is in the same direction as B in order to try to maintain the original flux. Okay, so B induced is going to be into the screen in the same direction as the magnetic field due to the current in the wire, in the straight wire. So by the right-hand rule, I put my thumb in the direction of B induced. It's downwards or into the screen, let's say. And my fingers loop around in the clockwise direction. And so we must have an I induced that's going around in this clockwise direction to create that B induced. Okay, and so both of these problems are just practicing applying Lenz's law to determine the direction of induced fields, induced magnetic fields, and induced currents. Let's see if we can find a question that is quantitative, so we can actually do a calculation. So let's see, I'm going to try to get rid of all of this. And we'll get rid of this. Okay, all right. So this question says, suppose we have a coil with 50 turns and it lies in the plane of the page. There's a uniform magnetic field that is directed into the page. Okay, so let's draw some of that. We'll draw the magnetic field that's going into the page. So those are the feathers of the arrows that are flying away from us. So here's our magnetic field. And it's uniform, constant, not changing. All right, and then we have a coil of wire, but we're gonna say that this coil has like 50 turns. So I'll just draw a bunch of loops. Okay, so this is N equals 50 turns. All right, and the coil has some area. A is 0.250 meters squared. All right, so this is our initial situation. Let's go ahead and let's calculate the magnetic flux through this coil. So let's calculate the flux through a single turn of the coil. So I'm going to call that phi1. So the little subscript 1 means that we're calculating the flux just for one of these loops, keeping in mind that we have 50 loops in total, but let's just focus on one of them for now. The magnetic field is perpendicular to the plane of the loop. So when we evaluate the dot product, we'll just get the cosine of 0, which is going to be 1. So it's just going to be B times A. So that's all it is. And then we can say, since we have N equals 50 turns, the total initial flux is, so we'll call it phi B, is going to be N times phi 1, which will just be N times B times A. Okay, good. So what we're going to do then is we're going to take this coil and we're going to grab it by, say, the top and the bottom, and we're going to yank on it. So we're going to stretch it, and as we stretch it, the circle will collapse into a little line that has no area. So we'll say this is going to be our final situation. We'll have our magnetic field going into the screen. And we're just going to grab our coil and we'll pull downwards from the bottom and we'll pull upwards from the top. And when we do that, we end up with kind of our coil stretched out here. I guess it would be a little bit longer, right? Because we're going to pull the two ends, and so we still have our two little wires here. So now the area of the coil is 0 or very, very small. So that if we wanted to calculate the flux at the end, it's going to be B times A, but this is 0. And so our final magnetic flux is just going to be 0. So let's call this phi B initial, and we'll call this phi B final. We could put a factor of n in here because we have a 50-turn coil, but the area of all 50 loops is 0, so the total final flux is 0. So the change in magnetic flux is going to be the final flux minus the initial, which is just going to be 0 minus NB times A, or minus NBA. Okay, so that's the change in magnetic flux. We're told that when we stretch the coil, we do that process in 0.1 seconds. And they want to know what is the magnitude of the induced EMF. Okay. So anyways, that's what I'm going to focus on, is calculating the magnitude of this induced EMF. All right, so we know that the induced EMF, but by Faraday's law, is the time derivative of the magnetic flux, which I'm just going to write as the change in magnetic flux divided by the change in time. And we've already calculated the change in magnetic flux. I don't care about the sign. I'm just worried about the magnitude right now. So NB times A divided by delta T. N is equal to 50. B was equal to 1.5, was it? 1.5 Tesla. A was equal to 0.25 meters squared, and delta T was 0.1 seconds. If you put all those numbers in, let's see, what are we going to get? 50 times 1.5 is 75. Divided by 4, I don't know what 75 divided by 4 is, but it's 750, I think, divided by 4 volts is 187.5 volts. You could check that calculation, but I think if you put in the numbers, that's what you're going to find. All right, and so that's a pretty big voltage, and this example, what it tells us is that one way to amplify the effect of Faraday's law is by having not just a single loop of wire, but many, many, many loops of wire. And so if you add more and more and more coils, each one has the same flux passing through it, so that if there's a change in the magnetic flux, then you get an induced voltage in every single loop, and those add up. And so your induced voltage goes up by a factor of N, the number of turns that are in your coil of wire. And so that's how you amplify voltages that you get out of Faraday's law. That's why when we had this example of the generator, this simple generator has only a single loop of wire. And so the induced voltage or the induced currents that you would get would be very small if you're rotating this. When they build and design the generators that are used in these electrical plants, the coils that they spin in the magnetic field is not just a single loop, but it's many, many thousands of loops. And so that's how you can get these large voltages generated at these power plants. Okay, so let's see if we can find another question, maybe one that we can do a quantitative calculation. How are we doing time-wise? Oh, good, we got 10 minutes. So this will be our last example, and I've got a few others, and so what I'll do is I will just write out solutions to all of these other examples, and then you can work through them on your own, and you can check your answers against what I get. Okay, so in this example, what we're going to have is an MRI technician. So magnetic resonance imaging. This is someone who works at a hospital. These MRI machines generate large magnetic fields, and then you stick a person's body in there, and you can do some magnetic imaging. So what's gonna happen is this person who's working at this MRI facility has a ring on their finger, and they're gonna move this ring into a region where the magnetic field from the MRI machine is very strong. And we're gonna try to figure out how much current is induced in this ring, how much power is being dissipated by the current in the ring. Okay, so what we're gonna have is a 2 Tesla field where let's take this magnetic field to be coming out of the screen towards us. And so this is B is equal to 2 Tesla. And then we're gonna have a ring. This is the ring on the finger. And what we're going to imagine is that initially the ring was outside this field. And then it's moved into the field so that at its final position, we're sitting inside this 2 Tesla field. It said the finger is in the direction of the magnetic field. So if this was on a finger, the finger would be out pointing towards us. And that means the plane of the loop of the ring is perpendicular to the magnetic field. All right, and we're told that the ring has a certain diameter. That diameter is 2.2 centimeters. Okay, and the delta t, the time to go from initial to final is 1/4 of a second. All right. So A is, what are we supposed to do? Find the average EMF. Okay, so we're gonna find the average EMF is gonna be the change in flux divided by the change in time. So we'll do a similar calculation that we did in our last problem. So we have to take the final magnetic flux and subtract the initial magnetic flux. So the final magnetic flux is just going to be a ring is a single loop, so n equals 1. And then we have the magnetic field times the area. And the area we could write as pi r squared. Since we're given the diameter, I'll write the radius as d over 2 and then square that. So this is the initial magnetic flux. Sorry, no, this is the final magnetic flux after we've moved the finger into the magnetic field. Initially, the magnetic field through the ring was 0, so there was no flux. And then this all happens in a time of delta t. So what we end up with is pi times b times d squared over 4 delta t is the induced EMF. And if you put in the numbers, this comes out to be about 3 millivolts. So it's small. And this maybe gives us sort of, if we compare this to the previous example where we had n equals 50 for our coil, we saw a much bigger voltage, and that's the effect of having lots of turns versus just a single turn. Okay, so B is, let's find the dissipated power. Let's find the dissipated power if R is the resistance of the ring, and let's see, I want to pick a value. R is 0. Oh, no, okay. That's it, that's the next problem. I'll skip that. Let's as the last thing we'll do, let's see if we could figure out the direction of the current in the final position when we're moving into this magnetic field. So we went from zero flux to a strong flux that's coming out of the screen. So should B induced be into or out of the screen in this case? Who thinks it should be into the screen? There's one. Who thinks it should be out of the screen? Okay, so not many people voted, but more people voted for into the screen. And that's correct, because we initially had 0 for our flux. And when we move this into the field, we want to try to maintain that 0. And so we have to oppose the direction of the field from the MRI machine. So B induced is into the screen, and by the right-hand rule, if my thumb points into the screen, my fingers loop around in the clockwise direction, and so we must have a clockwise I induced. But this current will only be induced when the flux is changing. If I move the ring into this region of space, and then leave it stationary so that we now have a constant magnetic field through it, what would the current be? 0. So we only get the induced current and the induced magnetic field as the flux is changing through this loop. Once we're fully entered to that magnetic field, the flux is now constant, and d phi dt is 0, and you get no induced EMF. Okay. So that's where I'm going to stop. I hope you had a good term. I hope you have a good summer. As I said, there's a few more examples here, and I will write out my solutions and I'll post those with the notes that go online on the course website. All right, thanks very much.